morning. It's so great to see all of you. I mean that quite literally without the masks. Well, when I was asked to give this pit talk and came up with a title, I kind of ran long on it. And so I talked to organizers even just this morning and said if I can change the title, it would make it a lot easier, because I got wrapped around the axle on how, thinking it's going to be quantitative and fun with physics, and we don't want to do that on Monday morning. So I simply changed a little bit of edits and said, can subsurface imaging reduce risk? And that's where I'm going to go today, but I need two things from you, just two simple ones. One is I hope you can trust in me and the geophysics that I want to present from the perspective I've been doing a long time, and it would take a long time to explain us those. And just go past that to number two. Number two would be to worry about the purpose of the work. Sometimes we get focused on the task, but what's the purpose? And that's where I'm going to go with this. And it kind of starts clear back on my first day of work. And yes, this is a picture from day one. Welcome to field work and my field utility vehicle. January '86, working for the Bureau of Reclamation, doing cross-hole seismic testing, which was exactly what my master's thesis was, and I finished in August. So I was well armed with the first ASTM standard in geophysical testing. Got it, let's go do this. Went out, worked on Lake Casitas Dam, largest embankment dam in the Bureau's inventory, and I wrote a report. I was excited about that. I gave it to the engineers a couple weeks later. I walked up to the 9th floor. I met an engineer who'll go unnamed, but let's call him Bob. And I said, how'd you like that report? Were those data useful? Did they get you what you needed? He pulled it out of his inbox, flipped through it, and put it in his outbox, said, we don't use that, we just have to keep the geophysicists busy. My tail quickly between my legs, I ran out of the 9th floor and decided what I have to do today is share with you the end conclusion of my entire talk, because I might run out of time, right? So I'm going to fast forward to last week. Some results we presented to CDOT for one of a project bridge going up on an interstate, and we only have two in Colorado, so 50% right on guessing which one. And I hope you can see the inlay there of the bridge that's proposed with some borings and CPTs and SPTs, things like that on this. So we're integrating the data. But what we got when we presented the data was this from the client. Said that these data can change the design and the cost of the project. I'm going from not used to changing costs in 36 years. Took a little while. So what I want to do today is spend time with you, because everybody lives in this. This whole room lives with this, right? This is the range from lots of dollars to barely any, and I draw like the person on the right, and I actually live there as a consultant. And in geophysics, sometimes that's what we get too. But all of you, whether it's drillers or anybody else, and using your data from the labs, we're all looking for one thing, the return on that investment, the value that we'll get back from what we're doing. What is the benefit of what we're doing for our infrastructure? Is it really there? We all want to run like the thoroughbred from Kentucky, but often we're stuck with stick figures. So the benefit can be shown from this NCHOP synthesis. It really broke down projects and the cost overruns and how much money was spent up front. It's a terrific synthesis. If you spend time on it, the axes, there's a lot to this graph. But really, this upper bound to me was something about the risk threshold that you're willing to live with on how much you spend up front in order to get the subsurface characterization right. So I'm going to jump into projects, and I'm going to go through them quickly because I really want you to just see why we're doing this. This is a solar farm. I'm going to spend time on renewals very quickly. This is a frequency domain EM project. I won't spend any time on that, as I said. But we can see shallow with this instrument. We can see intermediate, and we can see deep. And we won't know until we start learning the geology. So when I flip through this, going back, you can tell there's a difference, can't you? Whether it's shallow, intermediate, or deep. And the real crazy part about this is I learned a new word. This project was being done for bankability. Never heard it till 2021. And when that became the purpose of this, I started realizing there's an elephant in the room. Anybody point to it? Yeah, it's that. The colors, Peggy. So what we're up against is trying to help bankers or engineers that don't understand what FDEM is, or even conductivity. What's a millisiemens per meter, Phil? Well, what we've got to do is we've got to take that and turn it into something you can use. Make it useful, make it valuable, so we turn it into a depth of the limestone, because that's what this is about. So what I'm going to show you is the final product given to the client on this report. Wait a minute, I lied. Final product, digital now. It's the shape files. It's the information that we can give in digital format, so it can go into your system, and you can decide hey, I've got this many acres, I could have to be prepared to pre-drill. I've got so many acres, I might have to pre-drill, but I might be able to drive my piles because solar foundations aren't really complex. But when we know we can do over 70% of it, just drive the piles, this project just became bankable. The success was in this figure, had nothing to do with the EM, but it's how we got there. And I say we because, as Brad mentioned this morning, it's a community. It's a geotech. It's the information that's actually on this map to do the statistical analysis to get to this from the geophysics. So I'm going to go do some little higher load kind of solar work, or excuse me, wind farm work in the renewables. And we did 3D seismic. And 3D seismic is like a Christmas present you can't see inside until you start unwrapping it in pieces and parts. And one of the ways we like to do it is we slice by velocity. The number here, 4,000, has meaning to it because it comes from the borehole logs, and we did hundreds of these sites, so we have it pretty well constrained. We feel like if we can say, hey, you know, this site looks like it's got uniform layering, it's pretty smooth surface at 4,000 feet per second, the top of the Blaine Formation in western Oklahoma. It's a simple layered model, really low risk. But then we get to another site and we start seeing on the outside of the package, something's changed here. And we strip away that 4,000 and above feet per second, below. It's not uniform anymore, it's not smooth, it's pretty rough, kind of bowl-shaped. So we got a moderate risk here. And site C looks a lot like site A when you get inside. Wait a second, this is pretty smooth layering. You strip off that 4,000 foot ISO surface and it's no longer that, it's rough, it's contorted, and now we've got a high risk. So what is going on here is it's the geotechs and the geologists and the engineers working together to come up with these risk assessments. It's not just based on geophysics, but one component, one tool. And no, that wasn't the worst site. This was in fact drilled out with 4 different holes, and evaporite karst was found. So when we play with these toys and we come up with our own assessment in a subjective world of geophysics, I come up with red, yellow, or green. And the engineers are doing the same thing, and the geologist was doing the same thing. And we got in the room together, and we brought those together and decided what could be done on this project site that I'll share in just a minute, because engineering judgment is going to finally be the key. So I'm going to move to eastern Oklahoma and do the same thing on a renewable, but it's different geology. I got to use a different tool. I'm going to use resistivity, try and find voids. And on site X here, we'll call it, really overall high resistivities, and the geologic sense is pretty good, and the anomalies aren't below the foundation, which is a pink circle in the middle, so it's low risk. You go to another one, it's a little wider range, and we start seeing features that are within the foundation, so it's a moderate risk. And then we get to ones that are high risk, where they're right below the foundation. And in fact, there's a tunnel that goes right through it that's found by the Oklahoma Splunker Society. Didn't know that going into this site. So the real result from those wind farm projects was that at the development stage, there was an unacceptable risk, and that project is not being built, but it was decided early. The other one, again, the geotechnical characterization, told us that, hey, we can go into construction, and I have the yellow there on purpose because we can go into there with an accepted risk. We know it's there, we know what we're going to do. Now I'm going to jump to a transportation project because I like to talk about the project life cycle, and sometimes they'll start with an emergency. In this case, an earthquake in 2017. The real problem on this one is how can you do this and not interrupt the tourist traffic? So the hole there is what was the problem. Does it go underneath the distressed highway? Yes, it does. We use 3D radar and 3D seismic. And the good part about doing fun science like this in one of the islands is they have to move fast, rapid. They got to get those roads back open. There aren't enough of them. Here, the risk was mitigated quickly in the assessment that we showed them. Rapid mitigation and design occurred quickly, and a $1.8 million fix ensued with no drill hole. For me, I got a little fist pump on that one. Talking to Camise, he shared with me that road was fixed and open and safe within less than 30 days from the earthquake. Jumping into other parts of our infrastructure, there's a craze to raise the dams instead of build new ones. 25 feet doesn't look like much, but 100% water use or water retention and resource is good. The right slide shows the image. If we're raising the dam, that's the new cornerstone, so you need some condition assessment, right? Built in 1908 to 1911. It's over 110 years old. Looks pretty good, at least it's standing. So what are we going to do? We're going to get on it, do a condition assessment, hang off one side, put some receivers, get on the other side, spank the face of it. We're going to do something that looks a lot like crosshole testing, which I told you I came from. And we're going to do this through dam seismography that I've mentioned. And we're going to get these kind of images and panels and colors again. Is that going to be helpful? Well, it's not going to be helpful until we go into your terms as engineers. We go after the UCCS and how that might relate to the VP that I measure, and we start saying, wait a minute, I'm going to help you answer your questions for design based on our color scheme. It's not going to be linear, but at least we can look at that color velocity scale now and think in terms of PSI. Last example, I have to hang it in space because I can't even tell you where it is. I wish I could. Beautiful site, let me say that. But what can we deliver from this? Three-dimensional digital models. What are we able to get from it? Something brand new. I took this picture in my conference room right next to my office. 3 of my young geophysicists are in the model. That's a long way from the rain at Lake Casitas in 1986. I'm looking at them and going, wow, they are walking through the model because BGC brought in all the geotechnical data, you know, the core recovery and RQD and you name it. It's in here, and we're making those interpretations. So I'd like to finish with what we see. Okay, geologist. I'm an observational geologist myself at heart. Became an engineering geologist, working for years at law. I'm sure there's some outlaws here, close to the world. But what are we going to do with it? How are we going to use that data? What's it going to do for us in the end? How are we going to be able to present this information to stakeholders in the way that Dr. Anderson shared in his PIT talk? I loved it. You get stakeholders to see it. You can explain how to use it every single time. So can we? Nope. All right, there went 12 minutes of my Saturday or Monday. Can't use it. Well, that's right. We got to remember Bob. Some people just won't use it. We got to know that it's done properly. A real important piece, and thank you A-Game and all the people, Silas and Derek and Ben that are working on that. And it's not used at the right time in the project life cycle. I believe earlier is better. It can help guide drilling. And then I'm going to say, absolutely it can. It can when we use it in conjunction with all the other geology and geotechnical information from a site. I won't look at it as the single tool and the single bullet. When implemented early in the project life cycle, as I mentioned, and when properly executed, how are we going to go about the work? Lastly, I'd just like to say, welcome everybody. I've had my whole life looking at a photo like this, but I change it just a little bit. Take nothing but data and leave nothing but footprints. I hope you enjoy your conference.